Um, and I will not really talk about all the mathematical aspects that are covered in the 2 sections because you've read them. But I will try to give you some examples from classical mechanics explaining why this stuff is useful. And the next chapter that you will be reading is on basically classical mechanics. So it defines Hamiltonian systems, what's called Hamiltonian vector fields, etc. And this book doesn't really do a lot of examples. So if you want to see examples, you should open like Arnold or something like that. Yeah, or Goldstein. There's a bunch of famous books on that. Right? So before you have to read that section, I will try to give some illustrations as to why it's interesting. Okay. And by the way, symplectic geometry is not just classical mechanics. It's been slowly seeping into basically all fields of physics by now. Quantum mechanics and quantum field theory. There's something called geometric quantization, which uses the symplectic geometry to explain what we usually do with quantization. And that turns out to be very important in quantum field theory on curved backgrounds, the stuff that Bob Wold does here. Okay. But the problem with symplectic geometry and why not that many people actually do it and apply it in physics is because it's a little bit difficult to imagine, right? It's not really as visual as Riemannian geometry, for example, because you will see there are. So I don't think we're going to do it in the material that I'm going to cover, but in actual applications, you have to think about stuff like Lagrangian submanifolds and then various symplectomorphisms, etc. And that stuff really is kind of orthogonal to all of the imagination that you usually use in Riemannian geometry, because if in Riemannian geometry all the fundamental objects are kind of symmetric like the metric, right? Then the symplectic form is anti-symmetric, and it kind of screws with the whole visual imagination that we have. But it is extremely convenient for Hamiltonian mechanics, for Hamiltonian descriptions of things, as you will see, and so it's hard to get away from it. Okay, so as I told you before, both Riemannian and symplectic geometry, they have a certain structure which is different in the 2 different geometries that gives you a natural isomorphism between tangent and cotangent levels. Okay. And this isomorphism is, in the 2 different directions. It's raising the indices, I guess. So in this direction, it's going to be lowering the indices, and in this direction, it's raising the indices, the musical isomorphism. But in general, these isomorphisms could be a lot of different things, right? And in Riemannian geometry, we have one special isomorphism, which is just given by the metric itself, right? So in Riemannian geometry, let's say, lowering of indices is literally just the metric, right? Lowering of indices is a map from vectors to covectors, which the metric is, if you leave this slot open and you put something into this slot. And in symplectic geometry, it's a different thing. It's a differential form, right? So how is that done? What is the definition of the symplectic form?
It's a 0-2 form. diffuse symmetric, non-degenerate.
Yeah, right. So, well, if it's a form, then it's automatically diffuse symmetric, right?
Yeah.
So the conditions are that it's a two form,
Yeah.
which is what, non-degenerate,
Yeah.
and what else?
Does it have to be closed?
Yes. So omega, the two form. Okay. Then d omega is 0, and it's non-degenerate, which means that if for any y, well, what notation does the book use for tangent vectors usually?
Tangent vectors?
Like v, w, etc. Doesn't
Most
matter.
definitions, I think basis vectors, just the e's.
Well, okay, if for any tangent vector at point m, omega of v and w equals 0, then w equals 0. Right? So these are conditions. Of course, non-degeneracy here is completely analogous to the non-degeneracy of the metric in Riemannian geometry, which is its positive definiteness as opposed to non-negative definiteness, right? Okay. And so non-degeneracy basically makes sure that there is an isomorphism and not just a morphism in one direction, right? How is this isomorphism defined in this case? Yeah. Oh, by the way, this is, of course, equivalent to the matrix. If you write down the matrix Wij in some basis, it's a tensor with two lower indices, right?
Right.
And it's going to be an antisymmetric matrix. The condition is that this matrix is invertible. It's the same condition. Okay. Okay. And here we have the invertible matrix Gij. So of course, there's absolutely no difference in the definition. Right? The lowering of indices is, again, it takes a vector vi and spits out a covector Gij. And so the raising of indices will be, I'll take alpha, I, and then spit out, sorry, not G, omega, and then omega inverse, right? Ij.
Oh, so that is our isomorphism between vectors and covectors?
Yeah.
Okay.
So again, this non-degenerate form is an object of the same type as the metric, right? It's just a covariant to tensor. So it allows us to raise, lower indices in a natural way. But because the matrix is invertible, there's also, the inverse tensor of type 2, 0, which raises indices. So usually we don't write omega inverse Ij, we just write omega with upper indices Ij for this. Just like we do for the metric. Although really it is the inverse tensor, the inverse matrix locally. Okay. And okay. How do I define symplectomorphisms then? So we now live in the category of symplectic manifolds, right? If we worked in the category of Riemannian manifolds, then morphisms between different Riemannian manifolds will be maps from one to the other, such that some basic structure is preserved, like the metric is mapped, the push forward of the metric on the first one by the mapping is equal to the metric on the second one. So obviously it's going to be the same in this case, but for differential forms, usually it's much more natural to use pullbacks, right? Because they are easier to define. They don't use the inverse of the mapping. So symplectomorphisms, I'll just write morphisms. In this category are maps from a symplectic, let's call it M omega manifold to some n omega tilde, such that the pullback of omega tilde equals omega. And of course, it has to be a diffeomorphism of the manifolds themselves. So that's natural. In classical mechanics, these things will be called canonical transformations. Basically, you can, because they are diffeomorphisms, and in terms of, if you just look at the manifolds themselves, they are basically identical. It's the same manifold, right? If two manifolds are diffeomorphisms, and there's no additional structure on them, there's no way to distinguish them, basically, right? So if you do have an additional structure on them, then now there's more ways for them to differ, right? But if there's a symplectomorphism like that, then again, they are basically the same manifold in this category. So all of this is doing is shuffling around the points on the manifold with preserving the additional structure of the symplectic form, which is basically, you can think of it alternatively as a change of coordinates on the manifold, such that it preserves the matrix of omega. Right? So it's a change of coordinates which doesn't fuck up any of the equations that involve omega. Right? And we will see that Hamilton's equations of classical mechanics are expressed in terms of omega, and so transformations of this type will preserve the equations of motion, which is why they're called canonical transformations. They're just changes of coordinates in the phase space which do not change the form of the equations. Yeah. One very important class of symplectic manifolds is provided by cotangent bundles of configuration spaces. Right? So, phase space. Yes. But it's important to realize that there exist Hamiltonian systems which do not have this form. So the symplectic manifold M in this notation can be anything. It's obvious that it has to be even dimensional, right? Yeah. If it's odd dimensional, then any two form on it will be degenerate. You can check. Hopefully there's a proof somewhere. Yeah, there's a proof in the symplectic algebra part where you look at the canonical forms of symplectic matrices, and their eigenvalues come in fours of lambda bar minus lambda bar, right? And if you have an odd dimension, then basically there's no space to put, extra, like 4 tuple, what's the quadruple, right? of eigenvalues, and so it has to be 1, 0. Anyway, so this class of manifolds is defined like this. This is a configuration space. Think R3, for example, right? The space of positions. And then M is going to be T star of Q. Right. And locally, this will have coordinates, which we can call Q and P. Right? Well, Q and whatever, some coordinates like that, right? So these are the coordinates on Q. These are the coordinates on the fiber. But they're not velocities, right? So this is important. They're not elements of the tangent. Maybe I should use log index. So momenta are going to be dual to velocities in a sense, and that's important. Of course, there's an isomorphism between tangent and cotangent, but you will see in a second why we use momenta here, and there's no way to implement velocities on the same footing as momentum in Hamiltonian mechanics. So why are they special? Why is T star Q special and not TQ? It's special because it has a canonical symplectic form. Right, so on a general symplectic manifold, there are many different ways to define symplectic forms, right? As many as there are closed non-degenerate true forms. But on this one, there's in a sense, tautological symplectic form, which is chosen. So, do you remember what it is?
In here, it's dp, which dq?
Right. Or dq dp. Which one does the book use? Obviously.
I'm reading Arnold.
Oh, okay. Yeah, I think Arnold uses dp dq, and then that book uses dq dp. Doesn't matter, of course. But okay. So really, this means locally in coordinates, this means sum over. So why is this form special? Why do I call it canonical? There's an equation which shows why it's canonical. It's tautological in a sense.
Is that the Darboux theorem?
Not really. This is before Darboux theorem.
Well, I think of it if you just have a cotangent space. Yes, and you're guaranteed a form of that.
Right.
Yeah.
But this expression doesn't really explain why it's special.
I don't quite understand special.
So okay, it's a tautological form in a sense. Tautological because it reproduces the vectors it acts on. Okay, so you can think of omega as something that acts on, let's say, a covector. One second.
Omega acts on true vector.
That's the right equation. Okay. I missed one step. Skipped one step, basically. First, you define this canonical form theta. Okay. Canonical one form. And this one is canonical because here's what it does. That's a theorem, I think, number 7 in that section. Okay. That theorem is written in a very convoluted way, but in local coordinates, theta is just PDQ. So imagine acting with this on a tangent vector.
Yeah.
Okay. Theta is a form on T star Q. So it acts on vectors tangent to T star Q. Okay. They have a lot of components. So you can take something like Q dot and then P dot living in T M, right? This will be a tangent vector. I mean, I'm not including the point it is attached to. So Q, P, Q dot, P dot, the coordinates for this. And then I can take, oh, okay, maybe I will write out the full coordinates. Okay. And then I will map this. I need to map this to a number, right? Well, look at what we have. We have T, which is a covector at this point, right? So this is in T star Q, Q, right?
Yeah.
And this is in T, Q, Q.
Q dot.
Yes,
Yes.
it's velocity vector,
Yeah.
right? So it's a tangent vector. So it can naturally, without any additional structure, I can just act with this thing on this thing.
Yeah.
P of Q dot. And this is a well-defined one form, obviously, and we're going to call it theta. And that's what theta does, right? So if you feed a velocity vector like this into this one form, dq turns into q dot, contracted with p. That's what it is. dqi just selects the coordinates of this velocity vector. Okay, so that's why it's canonical. I don't need to use any additional structure, right? It's absolutely natural. I have two parts of my bundle, and I act with one of them on the other. I get a number, so that's a one time. Okay. And then omega is just d theta, or maybe with a minus sign in the book, because d theta will be dp dq. Okay. So this is called the canonical one form, and this is the canonical two form, or canonical symplectic form. So in all of the basically college classical mechanics that you do, almost, well, not completely true, but almost all of the problems that you solve, they live on this type of a bundle. So the cotangent bundle of a configuration space. Or in the Lagrangian case, it's going to be the tangent bundle. But the difference is that in Lagrangian mechanics, there is no canonical one form like this. So this is why T star is special. It has a canonical one form and a canonical symplectic structure. TQ doesn't. There's no read to act. If this was TQ, it's not clear what to do with that. Okay. That is basically almost the end. But the Darboux theorem is also interesting because it explains, in a way, why it's so difficult to think of symplectic manifolds in your head. And if you go back to Riemannian geometry, for example, when are two Riemannian manifolds the same manifold from the point of view of Riemannian geometry? Right? They have to be diffeomorphic, and the diffeomorphism has to map one metric to the other metric. And that raises the question of, if I have a manifold, for example, then locally, can I choose, like, is there some canonical choice of coordinates which brings my metric locally to some canonical form? right? So it like diagonalizes the matrix, for example, in the whole neighborhood of my point. And that's possible, right? Because the metric is a non-degenerate matrix, so locally I can just try to diagonalize it at least at one point. Then if it commutes with itself everywhere, which seems highly improbable, then I will also be able to diagonalize it around that point. But you see, there's still a lot of free components of that matrix. So there's not really a canonical form. Like there is a canonical form at one point, which is diagonal matrix with the eigenvalues. But then on the manifold in general, there's no canonical forms. So there's a lot of freedom, and that means that there's a lot of different different manifolds. Even with the same base manifold, there's a lot of different Riemannian geometries you can create on it, right?
Even with the same metric.
No. So I mean, many different metrics, right? Which will not look the same after you pick convenient coordinates on the two manifolds, right? On the two copies of the manifold.
So is that why, like in general relativity, you could have like different coordinate systems? Like you have your, I guess you could like say normal Cartesian coordinates or Schwarzschild coordinates, and there's no real like preferred one. I'm not sure. I don't think I fully formed this question all the way.
Yeah, I mean, in Riemannian geometry, there's really no analog of the double theorem, right?
Oh.
There are a bunch of different coordinates, like you said, normal coordinates, and there's something called Fermi coordinates, I believe, along the curve. A lot of different stuff you can come up with locally, but it doesn't fully normalize the matrix, the metric.
But with symplectic geometry, there are very natural coordinates which are going to correspond to our position and momentum coordinates.
Right. So the Darboux theorem says that locally any symplectic manifold looks just like R2n with the natural with the standard symplectic form on it. Okay. So, and this is called, finding the coordinates for which the symplectic form looks like this is called diagonalizing the symplectic form, even though the symplectic form itself is, if you write it out as a matrix, it's not going to be diagonal. It's going to be like this. There's like blocks. Diagonal matrix here and the diagonal minus that matrix here. But since we only care about half of that matrix, basically diagonalization. This is why symplectic geometry is special, and it's a lot more difficult to think about these manifolds because it's not, the structure is not rigid at all. Like locally, it's always just dp dq, and that means that the properties that distinguish different symplectic manifolds from each other are mostly topological and not really geometric, right? Because locally they all look the same. So differences can only come from the global structure of the manifold. Right? So it kind of disperses the microscopic structure of the manifold. But that's why it's also more powerful and more widely applicable because it's topological, so it doesn't really depend so much on the details of whatever problem you're solving. So it can be applied in many different things, like Morse theory. Morse theory was a little remark at the end of the section in the book, which is a very big and important field of mathematics. Which Arnold has done a lot of pioneer work in. And there's still a lot of unsolved problems there. Okay. So maybe I should try to give you some examples. By the way, the one isn't calling. I'm not sure why. Didn't touch screen. Examples. And I will describe Hamiltonian mechanics really quickly. What's a good example? Okay, let me start with Hamiltonian mechanics, and then I will do examples. Then I can use Hamiltonians simultaneously with symplectic forms. So the first definition you will see in the next chapter is going to be this. Let's say we have a symplectic manifold, and a vector field is called a Hamiltonian. If there exists a function h, let's say smooth, such that if I plug in my vector field into the symplectic form, I get dh. And this is the first thing, the first definition where you clearly see the orthogonality of the visual picture that you need to keep in mind for this. In Riemannian geometry, like the natural definition would be, gradient h is equal to x. In Riemannian geometry, how we call this a Hamiltonian vector field, right? It's just literally the gradient of a Hamiltonian. Okay.
Yeah.
If you dualize this, gradient turns into dh. Dh is basically gradient. But then what does x dualize to? In Riemannian geometry, it would be the one form, x with the lower derivative, right? But in symplectic geometry, we don't have a metric, so I need to use omega. But omega is an antisymmetric object. So what it does in phase space, it basically, the most basic thing I can imagine, for example, is rotates the vector by 90 degrees in some way. Or more specifically, omega is dp dq. So what it really does is it kind of flips all the p and q coordinates, or it turns, basically does this. qp goes to minus p.
I'm sorry, what's the I subscript x thing?
The interior product.
Interior product?
Yeah, so ix omega is a one form, okay? And it acts like this. Ix omega of y acts on the vector, right? As omega of x. So it just plugs in x into the first slot of the form.
Oh, okay.
That's the index-free notation for x I omega I j.
Okay, makes sense. When you deal with differential forms, using the Einstein notation is a little bit inconvenient because there's a lot of extra components in the tensor, right? And if you just see omega, right, it's not clear if this is a form or a tensor, right? You need to remember that this is a completely antisymmetric object, etc. But in differential form notation, everything is usually clear, as long as everything you do is differential forms. Okay.
So that's that. So X basically has to be orthogonal in this sense to the gradient of H. And therefore, the flow along this vector field is going to preserve H. Unlike in here, it's going to be the fastest direction of descent for H, right? In this case, it's going to be the direction that preserves the value of H. It's a vector which is basically, in a sense, orthogonal to the gradient of H, right? Which means that it goes along the level surface of H. Do you know what level surfaces are?
Yeah, I understand until you switch. I understand how the switching of coordinates and the rotation is working out. And how does that you preserve it?
Well, there's going to be a theorem for it, but it should be pretty obvious. Let's say I take dH and I act on X, right? This is basically evaluating, this is just literally XH. Right?
Yeah.
This is the direction driven of H. But then dH is equal to Ix omega of X, right? Which is omega of Xx. But omega is anti-symmetric, so this is 0, of course. But the intuition for this is that the vectors orthogonal to the gradient of the function are the ones that they provide the directions along which that function is constant. They are tangent to the level surface of it. Okay. And so this is also called Hamilton's equations. And we write them in this form because in this form they are written coordinate free globally. But locally, we can only choose the most natural coordinates given by the Darboux theorem. So locally, we can rewrite them in terms of P and Q, and we'll get the usual Hamilton's equations. I'm not going to write it out, but it should be pretty clear from what I explained from this rotation already. Remember that this H is a function on this 2 n-dimensional manifold. Right? So this dH is the gradient in both P's and Q's. So the top here is going to be like dq by dH by dq, right, and then dH by dp. So this is saying that x I omega ij equals djh, right? And that's split it into 2 halves for j from 1 to n and from n plus 1 to n. Then it's going to be, so xi is a vector q dot p dot, right? And then omega is a matrix of this kind. It's matrix. In the canonical coordinates, right? Okay, in the book it's going to be. So when I act with this matrix on this, I get
the usual one.
maybe I need to flip the indices here so it's easier to think of this as multiplication by indices.
Yeah.
If I write J, I put a minus here, then this is the usual multiplication by matrix, and then minus p dot q dot, and this is dh by dq, and dh by dq. And that's your Hamilton's equations. So we are, for now, considering time-independent systems. As you can see, the symplectic manifold doesn't involve, it's even dimensional. There's no time in it, right? And the Hamiltonian is only a function of p's and q's. It doesn't depend on time, which is why h is preserved, is conserved along the integral curves of this vector field. Cool. And you can also compute one interesting fact, which is that if x is Hamiltonian, then the flow of x preserves omega. That's pretty interesting. So this is a certain compatibility that follows from the definition. Okay. So this is saying that the evolution, if I fix a Hamiltonian, then that defines a unique Hamiltonian vector field for it. This vector field, or the one. This is saying that the flow of that vector field, which is literally the evolution of the system, right? How positions and velocities or moments change in time, is a canonical transformation. So the flow of that vector field preserves the form of the equations themselves, which seems kind of a tautological statement, right? Because the equations are the same for all t. There's no explicit time dependence in the equations, but yeah, that's what it's saying. And there's also a canonical volume form on any symplectic manifold, right? You can define volume proportional for some constant of proportionality. You can just take omega, that's a 2 form, right? And we know that the manifold is 2n-dimensional. So if I raise it to the nth power, by which I mean wedge it with itself n times, then I get a volume form. And it's guaranteed to be a volume form because omega is non-degenerate. So this is not going to be 0.
Does it have to be n times or 2n times?
N times, because this is a 2 form.
Oh,
So this
okay.
is going to be a top form. And so in the case of the canonical coordinates, the PDQ is just going to be literally the standard volume form on R2 and O2. And from this, it follows that Ft star volume is volume, i.e. the symplectic volume in phase space, right? Or it's actually called phase volume, is preserved by Hamiltonian flows, which is a famous and very important property. If you take the, I have an animation done in Mathematica a while ago, actually. But if you draw the phase portrait of the pendulum, do you know what it is?
Oh, I think I saw this in some of your 185 minutes.
Yeah. It's like a bunch of eyes, right?
Like, yes.
This is minus pi by 0. And you have a bunch of circles here. And then, here. And then carry it So it's really the phase space in this case is the pendulum itself lives on the circle. This is a circle, and then T star of the circle is diffeomorphic to the circle times 1, a cylinder. Right?
Yeah.
The phase space of the pendulum is just a cylinder. It's this cylinder. You cut this here and then glue it, and you get a cylinder. Okay. And the phase volume obviously is just the usual area on the cylinder or the plane, and I can take like a patch of like an ensemble of pendula, right, in the system, like an ensemble of pendulums which all have the same phase vector, right, but with different initial conditions. I'll put them here and start the evolution and look at the flow of this patch of volume. And we'll see that the pendulums that are closer to the separatrix here, they rotate slower, right? Because the frequency is dependent on the amplitude, and the higher the amplitude, the slower is the frequency, right? So these guys are going to lag behind these guys, and then you will end up with like a very long, like a spaghetti type thing after a bunch of rotations.
Is that like Liouville's theorem or something like that?
Right. So it'll get smeared out. It'll be like literally like spaghetti all over this strip here. And even though it looks like spaghetti, the volume of that thing is going to be equal to the volume of this initial patch. And that's Liouville's theorem.
And they separate.
This is Liouville's theorem.
And they separate.
What?
And the volume separate.
And the volume what?
And the volume he disconnected and still.
No. Oh, yeah. The volume of absolutely any set,
yes,
which has a volume, is preserved.
But I mean,
the volume from
so can the sphere be separated in the volume?
Is the question like, can you get holes in this thing in the process?
Yes.
No. Because the flow is a different marker. If everything is smooth, then the flow is a different marker. It doesn't change the topological structure of the volume. Okay. Yeah. When I learned classical mechanics in my second year undergrad, the proof of Liouville, we didn't use symplectic geometry, and so the proof of Liouville's theorem was like you take the Hamilton's equations in this form, and you write out the volume as the evolution of the volume is given by the Jacobian of the flow, right? So you take P dot Q dot, write it out as a matrix acting on PQ locally, right? Over infinitesimal times, you can just take derivatives of this mapping and take the Jacobi matrix of this mapping and compute its determinant. And then you expand the determinant at small times. And because of the nice anti-symmetry properties of the matrix that you get there, because basically this minus the determinant of this matrix, which is basically this flow here, is at small times, so like dt is going to be 1 plus big O of dt squared. So all the first order corrections just die out. But if this is the case, then you integrate this over any finite amount of time. The integral of dt squared is for 0, so it's just 1. But it's a fairly long. You have to compute the term. But it's a Flecky geometry. An immediate consequence of the definition. Or not the definition, but we just rewrote the same equations in a nicer form, it becomes obvious. Okay. Yeah. What else? Yeah. So I should probably give you an example of a system where the symplectic manifold is not T star Q. The problem on which I'm working for my PhD, for example, is like that. Hydrodynamics. But in college, you also hear about one problem of that type, and that's called rigid body motion. Do you remember the equation of motion for rigid body motion? There's only one, Euler's equation, right? What are Euler's equations?
This was the stuff I had the most trouble with in one of so I don't remember.
That is as we get closer
So those equations. So you take the rigid body, right, and you fix a frame, which is kind of glued into the body itself. So it's going to be a non-integral frame because the body is rotating. But you have a angular velocity vector in the normal physical space, right? Which is going to have a different, it evolves somehow in the physical space, and then it evolves in a different way in the frame of the body itself. And the Euler's equation describes the evolution of omega of this vector in the body frame. So omega dot equals equals what? There's one more thing, which is L, right? L equals IMX, right?
So, is this torque times moment of inertia times torque, or vice versa? Wait, inertia consuming times torque, is that it?
What is that? Not really. Oh, what torque do you mean?
Oh wait, that's yeah, that's an equation for non-inertia.
But anyway, the equations are like something,
I was trying to think of
something
something.
to that effect. I forget what the matrix form of it is. But it doesn't actually matter what the equations are for me. It matters that if you look at the equations, there's only one time derivative there. It's a first order equation. Whereas usually in mechanics, equations of motion are second order, right? And this is unusual. And that's because the symplectic form here is different. There are no momenta in a sense. There are no momenta there. Omegas are the coordinates in the system. And this is the velocity in the space of omegas, right? So initially, when you only start describing the rigid body motion, you start with the usual thing, of course, where every point is moving, there's a coordinate of it in space, and it has a velocity, etc. But then at some point you forget about that, and you go to using only angular velocities and angular momentum. And that's when there's like a lot of magic happening behind the scenes, a lot of stuff. And it's related to the geometry of the group. So 3, the motion of a rigid body is actually a geodesic motion on the group SO3, SO3 under some natural metric given by the Kelvin form, if you know any groups. My point is that the symplectic form here will be given only in terms of omegas. And there's no way to separate them into different moments, into coordinates and moments. So I'm going to give you a simpler example where, okay, also one more note, to define a Hamiltonian system, you need 2 ingredients. Not just the Hamiltonian, well, first of all, you need a manifold, obviously, but then you need not only Hamiltonian, you also need the symplectic structure. If you don't have the symplectic form, you don't have the equation, right? Even though it might seem like the symplectic form is always dp dq, right? It's not clear. It's not always clear unless unless your manifold is d star q. It's not always clear what q's and what p's are. Okay? So it's important to remember that the symplectic structure is an element of this soup. Okay. And let's consider a free electron in a magnetic field. Okay. So I'm going to say that I have a plane, and my electron is moving, and the plane is constrained to that plane. Right? And then the magnetic field is orthogonal to the plane. So I have coordinates x and y here. And we can describe this in different ways. So one is 1. The symplectic form is the standard symplectic form, which is dx dpx and then plus dy. Okay. And the Hamiltonian is g squared over 2m. And that's not all, right? This is just literally a free particle. There's not going to be interaction with the magnetic field here.
But don't you normally
Wait.
put it inside?
And where?
You normally include the vector potential inside.
Ah.
Legal metric. And that's how
Mhm.
involved in that.
Right. Yes. So I replace the momentum with what?
Minus QA.
Minus E over C.
Yeah.
Okay. Alternatively, this can be made up to some coefficient. It's A times the velocity. I'm using the velocity, but of course, velocity and momentum in this case go pretty fast. I'm not talking about the time.
Yes.
Okay. That's one description. But of course, the problem with this is that it's not manifestly gauge independent, right? Gauge invariant. Although it is after you write out the equation of motion, and that's really all that matters. There's a little problem in geometric understanding of why is it dependent on the gauge.
I said it does have positive. Like what are not positive.
That's not a problem, though.
Yes, it's not a problem. It's not.
Yeah.
It is different from classical ENM in that hardness field field the effect of the conventional outside.
Yeah.
But I mean, this is like
And yeah, and this can be used to derive from that. Yeah. But the problem is that the vector potential and electromagnetism in general is a purely geometric construct. You can do principal fiber bundles and like connections and etc. curvature fields to define vector potential and magnetic field, and then they are completely geometric objects. And it doesn't really make sense fundamentally to mix geometric objects with this physical quantity, energy, in this specific way. So what you can do is you can take dx, dx, dy, dy, and then plus d dx, dy. You just add. The magnetic field is naturally a two-form in general. A is one form, and B is dA. So two form. But A is not physically, at least in classical mechanics, it's not measurable, right? So B is the physical quantity because it's gauge invariant. Right? And even though that may seem like a contradiction, if A is not gauge invariant, then it doesn't make sense that we can measure parts of it using like Aharonov-Bohm effect, right? But if you look at the Aharonov-Bohm effect, what it computes really is like ADL. Yeah, it's a flux, which is really gauge invariant. Gauge invariance is just saying that A can be chosen up to a closed form. If I had a closed form, this B will fill it. If I integrate a closed form of a loop, then it can be 0 by Stokes time.
Yeah.
Right? As long as that loop is contractible in that time. Right? If it's like if this is happening on a torus, then you need to be careful. Like along a big circle, the input is not necessarily zero, even if the form is closed.
you can't apply what the field.
Yeah. Because there's no area that contour encloses. Okay, so let's try this, and then H is going to be this. And let's compute, for example, X.
I need to cut out. I need it for a few minutes.
Oh, okay.
Takes a lot out. So.
No problem. Yeah, I'm going to stop after this, I guess. Alright. Next up. How do we compute it? Yeah.
You see it?
Well, first of all, this part clearly doesn't really do anything, right? Because let's say the initial state is just stationary, velocity was zero. Okay.
Yep.
Then what the magnetic field is trying to do is it's trying to make this electron rotate. Okay.
Yeah.
This form just enforces that if there was no magnetic field, then we would give it some non-zero velocity in the beginning. It would go along a straight line. I mean, it's just a form of a free particle, right? And
yeah.
Hamilton is a free particle.
Yeah.
So these two things together, they just
That's
go along a straight line. Yeah. And then the magnetic field will turn that into circles. Yeah. Maybe I should leave it in. let's think. So I have form. Let's write out the symplectic form, right? So I have a two-dimensional configuration space and a four-dimensional phase space, right? So I have x, y, px, py, four entries in each phase. And the form is going to be, so I've got 0, 0, and then I've got b, right? And then I got x, px, 1, and y, okay. X, y, px. So I got x, px, 1, and I got y, py, 1, 0, and minus 1. No,
Yes.
okay. So now my vector field is going to be like this. Minus omega ij times velocity vector, which is x dot y dot dx dot dy dot, equals, I put a minus in because I didn't want to put the vector on the left part of the matrix. I had I, the way I wrote it before was I,
Yes.
but the usual matrix action is j.
Yeah.
And then this is going to be dh, i.e. dh by dx, which is nothing, and then I've got dx over m. Right? So I just need to invert this matrix. How do I invert that matrix? Maybe I don't. I will just write this out explicitly. So minus let's write out the two equations on x dot and y dot. Okay. It's going to be I can move this on this. I'm going to get b y dot, right? So minus by dot equals minus by dot plus px dot minus dot equals 0. And then this is going to be minus b x dot with a plus of b x dot, and then minus b y dot. And this, of course, describes a rotation.
Yes.
Obviously. So, yeah. Well, okay. And my point was that adding this term to the symbolic form produces the same. And in general, when you put a particle in a magnetic field, this is the more general, geometrically, the more correct, in a sense, way of putting the magnetic field into the symplectic form.
By more correct,
It's more manifestly gauge invariant, right? So it's more natural in that sense. Of course, both of these ways are more convenient in different situations, but useful to keep this in mind. And of course, I could have just dropped. What if I just consider this? This one. And then the Hamiltonian will be, so I want to eliminate the momentum altogether. And the Hamiltonian is going to be, let's say just some potential. Only potential. So this is useful for, sort of massless particles. Like there's no kinetic energy. Classical. So in this case, what would the equations be? You would have here ux derivative and uy derivative, right? All of this is just erased, it doesn't exist anymore. And this matrix is just this matrix. So you will get the same minus dy dot, but now it equals not dx dot, but ux and uy. So my velocities now are equal to derivatives of some potential. To reproduce rotational motion, for example, I can guess probably what the potential must be. I think it must be quadratic potential. Right? If u equals r squared, then gradient u, or over 2, then gradient u equals r hat, right, which is just r. And so this will be just equal to x, and this will be equal to y. And you can see this is the same rotation with the same frequency. So again, the same motion, but now in this case, I can take my phase space to be just literally the plane itself. Okay, so m is going to be just r2. And my symplectic form is just the area form with a coefficient. And it's not clear what the coordinates and momenta are. It is, first, I could say maybe that x is the coordinate and y is the momentum, but physically that doesn't make any sense. Why? Why would you break the symmetry of the problem like that and call the coordinates in this moment? If you want to go to the Lagrangian description, the problem, so the interesting point about systems of this type is that there doesn't exist a Lagrangian description of this. Because to go to the Lagrangian, what you need to do, Lagrangian is d2 dot minus h, right? Expressed in terms of only 2 dots.
So that's is the Legendre transform the same?
Yeah. At least in the canonical coordinates on these manifolds, it would be that. But here, it's not clear, we don't have a p. Right? So I could say, of course, let's say q is x and p is y, and then this will be y x dot minus h. But now h was a nice function of x and y, and in terms of the velocities, it was a symmetric object, even if I put the analog of the kinetic but this is not a symmetric object in x and y. The physical meaning of all of this is really broken at this point. But this comes up in hydrodynamics, for example, in compressible ideal fluid hydrodynamics. You can replace the motion of the fluid itself with the motion of only vortices in that fluid. Do you know what vortices are?
Yeah, I got fluid.
Oh, cool. So knowing how vortices move with time is completely equivalent to knowing the flow of the entire fluid.
What do you mean by the electricity evolution?
Right. But if, let's say, vorticity is 0 everywhere besides a finite number of vortices, I can imagine a fluid like that.
Yeah.
And then knowing how those finite number of vortices move gives me the flow of the entire fluid into the middle. And that is also a case of this type of this is called symplectic reduction. So you start with a system which is a conventional phase space like that, and then you use extra symmetries that the system has to get rid of the unnecessary coordinates or momentum. And in the case of hydrodynamics, for example, that takes you from the velocity vector field of the entire fluid to just the velocity vectors of just a finite number of vortices. And the equations describing the motion of vortices turn out to be first order in time, because the symplectic form for vortices is this. It's just the area form. The B becomes the vorticity of one vortex. The Hamiltonian is a little more complicated, but it's like the electric interaction in two dimensions between charges. It's the simple vortices. And in the rigid body motion, you start with you consider the normal classical standard differential form, symplectic form on this manifold, which is the energy is equal to what's the better mv squared, right? So I omega squared. But really, this is but this is L, so this is really L acting on omega. In the symplectic form, yeah, is it just dl to omega? I think it is. And here, L is a function of omega, so really this symplectic form is defined only in terms of omega. They are the only coordinates here. I'm gonna verify this, but the idea is that you get rid of basically by going into the body frame, you get rid of the extra angle coordinates that describe the orientation of the body in the outer space. Okay? And the description just reduces to omega in their first time derivatives. So that's also a special case of symplectic regression. And incompressible hydrodynamics, ideal hydrodynamics, is actually completely equivalent to this, although it's pretty difficult to realize. That's called the Arnold Euler equation. So the Euler equation, as you might have noticed by now, there are two different Euler equations, right? One Euler equation for rigid body motion, and the other Euler equation for ideal incompressible hydrodynamics. But Arnold proved that they are mathematically the same equations, just on two slightly different structures. One of them describes
You mean the incompressible, or the equation on the rigid body?
and rigid body. Yeah. So rigid body motion is geodesic equation, geodesic motion on SO3 on the group SO3. So SO3 is the group of rotations in three dimensions. So you can so the evolution of the body, you can think of it as just a rotation matrix depending on time. That depends on time. You start with the initial position of the body, and then it rotates in time somehow. And that rotation is given by a rotation matrix that goes from the initial state to the final state. And that rotation matrix depends on t. Right? So it's an element of SO3. So R of t is a curve in SO3. And it turns out that it's the real evolution of rigid body motion is literally geodesic motion on SO3 under some canonical metric. Sorry, not canonical metric. The metric given by this. Omega. Omega is basically R dot R inverse. Remember this combination? If I take a rotation matrix and I take its logarithmic derivative, which is this R dot R inverse, then the result is going to be a matrix like this, minus omega x, omega z, omega y, like that, right? Into symmetric matrix. And the components of that matrix are the angular velocity. And that's a tangent vector because it's R dot. And R dot is a tangent vector at R. Yeah. R dot R inverse is a tangent vector at the identity matrix because R inverse shifts everything back to the identity matrix. And so omega is just a vector at a tangent vector at the identity of the group, i.e. an element of the real. You were thinking about that. Reading it, but yeah. And so providing the metric is the same as defining dot products of angular velocities, and that's given by I. So the moment of inertia tensor is just literally the metric on the group SO3. And using this multiplication by matrices, you can extend it to the whole group. But yeah, so in this metric, this is going to be the geodesic on the group. And
what does it mean? I is a metric on, so that's its space of matrices, 3 by 3 matrices.
Yeah. So it's a symmetric, non-degenerate 3 by 3 matrix. It satisfies all the conditions of a metric on that vector space.
Yes, but
on the whole group,
in SO3, if you want to make an inner product.
Yeah, SO3 is the manifold. Omegas are tangent vectors to that manifold. Okay. This is a rotation matrix. If I take the time derivative of the rotation matrix, that's my velocity of the rotation. Right? You should read more about this expression. But the beautiful idea of Arnold was to generalize this to other groups. Consider an arbitrary group of this type. And hydrodynamics corresponds to the group as diff of a manifold. The group of diffeomorphisms of a Riemannian manifold that preserves the volume. Right? I told you last time that incompressibility is just the condition that the flow of that fluid is a diffeomorphism that preserves the volume.
Yes.
And the group of diffeomorphisms like that is called S-diff. And so you can think of the flow of the fluid, of an incompressible fluid on this manifold as a family of diffeomorphisms, depending on time. Right? They shuffle around the points of the manifold. And the energy associated with this, the Hamiltonian, is of course just velocity squared over 2. Well, times density. There's some density, and then basically phi dot well, Q dot squared of 2 integrated over the entire manifold with whatever the volume was. And again, this defines, because Q dot is basically the time derivative of this diffeomorphism at point Q, this defines a metric on this group as diff, and the flow of that fluid is going to be described by the geodesic flow on this group with this metric. And if you write that equation in some nice geometric covariant terms, general for any group, then that equation is going to be exactly the same for SO3 and the diff. So they are the same thing. It kind of makes sense, though, that SO3 and SDiff are locally similar, right? Because SDiff is like the rigid motion of a patch of fluid, right, locally. The volume is not allowed to change, just like SO3 preserves lengths and therefore volumes in three-dimensional space. This preserves the same things, but only locally on manifold. So naturally similar in that sense. And there's a lot of other famous equations which are later turned out to be also special cases of